All right, hello class. Let's cover the Diels Alder reaction. There are two very important partners in every Diels Alder reaction. First, there's the diene, a molecule that has two alkenes or two pi bonds. These pi bonds need to be conjugated for a Diels Alder reaction. The second partner is the dienophile. The dienophile, this refers to a molecule that's seeking a diene. The dienophile needs pi electrons that can be present from a double or triple bond. What's very important in Diels Alder reactions are counting the number of pi electrons reacting. All right, because the diene has two pi bonds each with two electrons each. All right, that gives me a total of 4 pi electrons. And the dienophile can only react 2 pi electrons. This can be a bit tricky. Double bonds have the 2 needed. A triple bond has a possibility of 4 total pi electrons. However, only 2 of the 4 are reacting in a Diels Alder reaction. So let's cover some facts of Diels Alders. All right, they're known as a 4+2 cycle addition. So when the diene and the dienophile react, they form a cycloalkene, and the ring that we get out is a 6-member ring. Conveniently, 4 plus 2 gives 6. So Diels Alder reactions are known for preparing 6-member rings. All right, Diels Alder reactions are percyclic, concerted, and synchronous. All right, percyclic is referring to the cyclic transition states that are present. The concerted processes are referring to one step, no intermediate. And they're synchronous, saying that the bonds that are forming and breaking, they occur in synchrony. All right, and this is not always the case for reactions that are concerted. But conveniently, Diels Alder reactions have all 3 of these attributes. All right. This is a very well-controlled array of pi electrons and orbitals interacting, and this allows a very well-defined stereochemistry. All right, this is a hallmark of percyclic reactions. So very quickly, let's take a look at the reacting orbitals. All right, the orbital from the diene that's reacting is the HOMO, and the HOMO stands for its highest occupied molecular orbital. So if I had to consider all possible molecular orbitals for the diene, the reacting one is the HOMO. This is the highest energy orbital that contains electrons. All right, there's some unique features here. If I look at the molecule really closely, I see that there's 2 shaded areas here, and there's 2 shaded areas here. However, in the middle between these 2 molecules, there's no, the shading is inverse. All right, so because the shading here is on the left side and the shading here is on the right side, they can interact. However, in the middle, they can't. And this is a very important feature of the HOMO of a reacting diene in a Diels Alder reaction. If I consider the reacting orbital from the dienophile, all right, and it's going to be referred to as this LUMO, and the LUMO is the lowest unoccupied molecular orbital, all right, we start to see that these 2 pi orbitals don't have any interaction, all right? Conveniently, these features allow the HOMO and the LUMO to be able to come together to bond. If I look here, I have this area of no shading that can react with another area of no shading, and I got this area that's shaded can react with this area that's shading. All right, I'm going to erase this, and we call these type of interactions symmetry allowed, and that affords a Diels Alder to form the bonds. All right. So not only do I have to have 4 pi electrons in the diene and 2 pi electrons in the dienophile, the orbitals have to have the right symmetry. They have to be symmetry allowed to allow Diels Alder reaction to occur. We're going to cover some other systems that we need to investigate whether there's symmetry or not, or no symmetry of the reacting orbitals to kind of determine if a percyclic reaction can occur. All right, so lastly, we'd like to discuss 2 terms to describe the electronic environments of our systems. The normal electron demand has very high electron density on the diene and very low electron density on the dienophile. Because we have very high electron density on the diene, we're going to be reacting as HOMO, which I've showcased in that example already given, and the low electron density of the dienophile is going to cause its LUMO, I'm so sorry, to react. However, we can flip that and have the reverse electron demand. where the diene has very low electron density and the dienophile has very high electron density. All right, I didn't draw that system out, but it's possible to have a reverse electron demand as well. The take-home point here is that you need to have favorable HOMO-LUMO interacting orbitals to kind of have a successful Diels Alder reaction. All right, and we can modify the electron density by having certain type of sustenance, and we'll cover that shortly. All right, let's study features of Diels Alder reagents. The diene prefers to have electron donating groups. We're going to classify electron donating groups with the letters EDG. Okay, these are atoms or functional groups that pump in electron density. All right, atoms that have lone pairs are electron donating groups, as well as other carbons. All right, carbon doesn't mind sharing electrons with other carbons. What's important to consider is the location of where we place the EDG. And the structure that is drawn, we're going to call that position A, and the EDG is located internal to the diene. However, I could draw another structure where the electron donating group is on a terminus carbon, and we'll call that position B. Okay, sure, there's another double bond or alkene in the structure, but there's only 2 carbons in every alkene, and that leads to only 2 positions, either internal or on the terminus. All right, so this is why there's only 2 positions and not 4 to consider. If I also need to consider some orientations of the diene to be able to react in a Diels Alder reaction must be able to adopt a S-cis orientation. All right, that's very important to consider. If your diene cannot adopt that conformation, it cannot undergo a Diels Alder reaction. We'll study some reactions of some systems where we need to investigate that later. So cyclopentadiene is extremely reactive because it's locked into this S-cis orientation. However, this molecule drawn here is not as reactive because there's an unfavorable methyl to methyl interaction or steric interaction. So this diene is a little less reactive than others because of that interaction. The other partner in Diels Alder reactions is the dienophile. Dienophiles prefer to have electron withdrawing groups. We're going to specify that with the letters EWG. All right, and these are atoms or functional groups that prefer to remove electron density. Groups that are extremely electronegative, as well as pi bonds. And pi bonds to atoms that are electronegative are extremely electron withdrawing. Atoms that have formal plus charge or atoms that are electron deficient are also electron withdrawing groups. We're going to be studying this more in detail in the next chapter, what type of functional groups and atoms or EDGs or EWGs. All right, so we mentioned that we need to, I guess, sincerely consider the positions that we have our electron withdrawing groups. If I look at this system here, I'm going to have my methoxy group, which is an electron donating group, in position A. Through resonance, I realized that the carbon, the adjacent carbon, I guess you would say, has a buildup of negative charge. So this carbon is extremely reactive. It has an increased electron density. If I consider the electron donating group being in position B, again, it is my methoxy group. If I investigate through resonance, the carbon all the way at the end of the system has the negative charge. So this carbon has this increased electron density and it becomes extremely reactive. All right, I can do the same consideration for electron withdrawing groups. If I look at the resonance, all right, instead of having a buildup of a negative charge because I'm pulling electrons density away, I'm going to have this plus charge, and the plus charge is built on the neighboring carbon. All right, so that means that that carbon becomes extremely reactive. All right, so knowing where the electron density lies, if it's extremely rich or extremely poor, is a very important feature to start to consider when we consider products that come from Diels Alder reactions. All right, so let's review that really quickly. If I have a electron donating group in position A, again, we're going to say that this carbon that's adjacent is going to be our electron or our reactive carbon, electron rich carbon. If I consider having an electron donating group in position B, then there's going to be the carbon at the end of that system that's going to be reactive. And if I have an electron withdrawing group, I make the neighboring carbon, all right, the reactive carbon. So let's consider the mechanism. The mechanism is straightforward. I'm going to have the 4 pi electrons reacting with the 2 pi electrons in the dienophile, right? So the arrows are showcasing that these 2 pi electrons are going to end up making a bond to one end of the dienophile, and the pi electrons in the dienophile are going to make another bond to the end of the dienophile, and the pi electrons in the dienophile are going to fall to make a alkene there, another pi bond here. All right, so this is why I get out this cyclohexane or cyclohexene ring. If I have a Diels Alder reaction with a triple bond, and again we said that the dienophile can only react 2 of the pi electrons here, we're going to end up leaving behind a pi system, all right, from the triple bond. So these are some very important features to consider in Diels Alder reactions. Now let's consider stereochemical control in Diels Alder reactions. The orientation of the dienophile is always reserved. So if my substituents are trans, they should be drawn trans in the product. If my substituents are cis in the dienophile, there should be cis in the product, all right? And this is also true for substituents of the diene, okay? They are also reserved. So we like to specify, or I guess kind of notate, that these 2 methyl groups will be on the outermost area of this diene, all right? So in the product, they're going to be cis to one another. However, I could have one substituent outside and one substituent inside the area of the pi system here. That's going to afford those 2 substituents to be trans to one another, all right? So let's review really quickly what happens if I react with a double or triple bond dienophile. Again, the double bond dienophile, this affords a 6-member ring with only 1 pi system. The triple bond dienophile affords the 6-member ring with 2 pi's. Okay? So, what happens if I have a cyclic diene? All right, I'm going to get a bicyclic addict or a bicyclic product that comes out of this. All right, here. So if we look at the 5-member ring, I get this bicyclic 2,2,1 heptane structure. All right, so if we look here, we see that there's one carbon that's circled in pink here. It's the one carbon that's kind of poking out of the face of this ring. All right, it's not participating in the Diels Alder reaction. If I take the cyclohexadiene structure, I get the bicyclic 2,2,2 octane structure. All right, and again, the carbons that are circled in red and blue are 2 carbons that are not participating in the reaction. All right, so cyclic dienes will always afford bicyclic products. What happens if I have a cyclic dienophile, all right, instead of getting bicyclic compounds here, I just get fused rings, all right? So in the example that I see here, these 2 rings are fused, so I have now 2 6-member rings fused together. So this leads to a possibility of these 2 attributes being combined. So I can have a cyclic dienophile and diene. And in that case, or in those cases, I will get a fused ring and bicyclic, all right? So I have drawn this both in the 2D and 3D. I think it's a little bit easier to see that in 2D, so that I have this bicyclic compound that's fused to this 5-member ring here. Okay, now let's discuss regioselectivity of Diels Alder reactions. I can take a look at these 2 partners where the electron donating group is in position A. All right, for my discussion of resonance, the adjacent carbon has an increased electron density, and it's going to be our reactive carbon. All right, and the carbon at the end of our dienophile is also a reactive carbon with a decrease in electron density. These 2 carbons are going to prefer to meet, and it would lead to substituents having a 1,4 relationship. Diels Alders of this type lead to the 1,4 major product. I can have a different set of partners where the electron donating group now is at position B at the terminus. We know that the carbon at the end of the system is the reactive carbon due to resonance, and the carbon at the end of our dienophile is also reactive. All right, these 2 carbons prefer to meet, and they lead to substituents having a 1,2 relationship. So Diels Alder products of this type leads to the 1,2 major product. All right, let's take a look at a few examples. I have these two partners where I have this old Tibbs group, which is an electron donating group in position B. All right, so that's going to push all the electron density to this carbon at the end. And the carbon at the end of our dienophile is also reactive, all right? So these two carbons need to meet in the product to be able to properly draw the major product, all right? Let's not forget the rules that we know from drawing major products from Diels Alder reactions. If I have a cyclic diene, that's going to lead to a bicyclic compound, and I need to make sure I showcase the endo-stereoselectivity. Okay, so if I look here, this carbon and that carbon met, that led to my two substituents having this 1-2 relationship. All right, I'm drawing this aldehyde down. All right, this is inside this concave face. This is indicating endo-selectivity. All right, very importantly, what we learned from this reaction is that any substituent at position B would have a cis relationship to an endo electron withdrawing group. Right, that's very important to keep that in mind. It's very easy now to start to see or start to draw the proper selectivity from these type of reactions. So let's say if I take this molecule, I have my Tibbs at position B, which is an electron donating group, and I also have a methyl group, which is an electron donating group, at position A. All right, so both of these substituents are pushing electron density here. All right, and at the end, the carbon at the end of our dienophile is also reactive. All right, so to properly draw the major product from this reaction, these two substituents or these two carbons need to meet. All right, and they do. That leads to the Tibbs and the aldehyde having a 1-2 relationship. You can see that by the pink numbers. And the methyl and the aldehyde has a 1-4 relationship. So I have a combination of the two effects here, leading to this being the major product. All right, I'm going to erase some things here. Very importantly, the stereochemistry of the diene is reserved. This Tibbs group is located outside of this pi system, but this methyl group is located in. So they are opposite faces, or they are trans to one another. And if I look at the product, the Tibbs group and the methyl group are trans to one another. And so all the stereochemical information is carried over correctly. Again, Tibbs and the aldehyde substituent have to be cis to indicate endo-selectivity.